Hey everyone, ever wondered how AI is getting better at solving physics problems? It's not just about crunching numbers, it's about thinking like a human. Today, we're breaking down a groundbreaking study that's changing how we train and test AI in the world of physics. Let's dive in. So here's the thing. AI models like GPT-4 or Gemini are amazing at pattern recognition. But when it comes to physics, where you need to juggle equations, real-world principles, and step-by-step logic, they often stumble. Why? Because physics isn't just math, it's about understanding how the universe works. And that's where this study shines. The researchers created a massive dataset called PHYSICS EVAL, 609 physics problems, all carefully selected from textbooks and online resources. Think of it as a supercharged exam for AI, designed to test not just answers but reasoning. But here's the twist. They didn't just want AI to solve problems. They wanted to teach it how to check its own work, like a student reviewing their homework. How did they do it? Two clever methods. 1. Self-correction. The AI solves a problem, then pauses to double-check its steps. 2. Multi-agent teamwork. A team of smaller AI models work together. One solves the problem, others act as reviewers, catching errors and refining the answer. Let's break it down with an example. Imagine the question, how many photons does the sun emit per second? It's a multi-step problem involving Planck's constant, the speed of light, and energy calculations. When researchers tested these methods, models that initially struggled started performing way better. The multi-agent system, in particular, crushed tough problems by combining multiple perspectives, like a group of experts cross-checking each other's work. But here's the kicker, not all methods worked equally well. Self-correction helped some models, but others regressed, making new mistakes when they tried to fix old ones. It's like proofreading your own essay and missing the same errors you made the first time. Meanwhile, the multi-agent approach consistently boosted scores, especially for complex problems. What makes this study special? The dataset is publicly available, so researchers worldwide can use it to build smarter AI. And the results? They show that collaboration, even among machines, can lead to smarter, more reliable solutions. So why does this matter? If AI can master physics, it could revolutionize education, engineering, and even space exploration. It's not just about fixing errors, it's about teaching machines to think more like humans with careful reasoning and teamwork. Now, let's dig deeper into how researchers actually evaluate these AI systems. It's not just about getting the right answer, it's about understanding how the AI arrived there. Imagine an AI tackling a physics problem. If it grabs the wrong numbers, like thinking a ball weighs 10 kg instead of 2 kg, it might still get the right answer by accident. But that's not real understanding. That's where mathematical accuracy comes in. We check if the AI's numbers line up with the ground truth, the textbook solution. If the data's off, even perfect math doesn't count. But numbers alone aren't enough. Think of an AI's reasoning like a recipe. If it skips steps, mixes up ingredients, or uses a totally different method without explaining why, it's hard to trust the result. That's logical consistency. The AI needs to show its work, step by step, in a way that matches physics rules or clearly justifies a new approach. What if it solves the main problem but misses the tiny details? Like ignoring a hidden constraint or leaving a sub-question unanswered. That's where completeness matters. The AI has to tackle all parts of the question, not just the obvious bits. Even if the math is right, if the explanation is a jumble of words or uses confusing terms, it's like a teacher who knows the answer but can't explain it. That's why clarity is key. The best AI solutions are easy to follow, avoiding unnecessary complexity and making the logic obvious. Now here's a tricky one. Did the AI use the right formulas? If it's solving a problem about gravity but pulls out a formula for electricity, that's a big red flag. The AI has to not just remember equations, but apply them correctly for the situation, like knowing when to use Newton's laws versus relativity. And what about assumptions? Every solution relies on some guesses, like assuming a frictionless surface. But if the AI ignores gravity in a free-fall problem, or makes wild, unstated assumptions, that's a problem. Good AI explains its choices and justifies them. Finally, overall correctness is the final grade. Even if some steps are right, a fundamentally flawed approach can't earn a high score. It's about the big picture. Does the AI understand the problem, or is it just guessing? Let's look at a real example. An AI solved a problem about a toroidal inductor, but assumed energy density was uniform throughout the coil. The real solution. The magnetic field varies inside a toroid, making that assumption an approximation. The AI got a thumbs up for its logic, but a heads up for oversimplifying. This isn't just about grading AI, it's how we train smarter machines. By breaking down solutions into these criteria, we're teaching AI to think like humans, not just memorize answers. And here's the kicker, this isn't just theory. Researchers are using massive datasets, like one with 19,000 physics problems from top textbooks, to fuel this training. Each problem is broken down into its core parts, with simplified versions to help AI focus on reasoning, not jargon. These datasets don't just list answers, they track everything, from step-by-step reasoning to edge cases. It's a goldmine for training AI to handle the messy, real-world complexity of physics. So next time you see an AI solving a tricky problem, remember, it's not just guessing. It's learning, checking its work, and getting smarter every day. Thanks for watching, stay curious, and we'll see you in the next video.